Yes, hi, everybody who's still here this late in the day. I'm going to speak about a new kind of map, new type of collection in 213. It's sequential maps, so but I'm going to focus on the immutable ones, but there are also one mutable implementation. And the challenge with those kinds of maps is that you want to keep the order while still using basically using a hash map, which is not ordered. So that's what you're trying to solve. Yeah, so we're going to look a bit about first an introduction, then we go through the challenges. Going to look at some of the implementations, both the ones in the 213, but also a set of other possible implementations, because there are quite a few ways of implementing, especially the immutable ones. We're going to look a little bit about how you can benchmark these kinds of implementations against each other, and also which tools to use, or which I used anyway, and have a look at the results, see what came out of the benchmarking, and also a little bit about how it is to start contributing to Scala especially. Yep. So, my name is Möller. I'm from Sweden, Stockholm. I've been using Scala since, I don't remember really the year, but it was version 2.7.5, I think. So it's over 10 years now. Yeah, and I've been coding since forever almost. So, but now the last 10 years almost exclusively in Scala. So what is a sequential map? Yeah, it's a new type. It's added into 13, and it's an interface or a trait called SeqMap, and it exists both as a general type and also as a like one mutable version and one immutable version, as is common in the collections library in general. It's like a regular map, but the entries are ordered by insertion, not sorted. So it's basically the way the series of events that you put stuff in, they remain in the same order. So no external ordering function is needed. So you don't have to have an ordering. The order is based on the operations you perform. And there are both mutable and immutable variants. Even though SeqMap is a new trait, there have been a couple of implementations around for quite a while in Scala, as we'll see. So what can you use them for? Well, anytime you need the entries of a map to have a stable ordering, so you want them to remain in the order you insert them, regardless of like if you restart your program or whatever, you still want to have a defined order. Like a hash map, it can be reordered on each restart, so it's very unstable, but this one is stable. And you can represent hierarchical data, such as JSON, even though JSON isn't ordered, but it's still nice to have it ordered, or XML or other stuff. And you can also use them for keeping, like, you want a map that's maybe 1,000 items or entries long, and you want to remove the oldest one you have all the time. So today we'll look at some different ways to implement a SeqMap. We'll look at their internal structure a little bit. We'll look at the benchmarking results for some of the more important operations. We'll see how they differ performance-wise for those operations, and also a little bit about the memory usage. And hopefully you'll get an understanding of the trade-offs between the different implementations, so you can say when to use which. Yeah, and of course there's challenges with especially the immutable ones. And the basic thing with the SeqMap is that it fulfills two separate roles. It's a mapping when used for key-based operations, so such lookup and other stuff. And it's also an ordering. So there's an index-based mechanism to look up or iterate through something. And that's, so you need to fulfill both those roles. And an optimal implementation would have a single representation for both those. of course, and while still having the best possible, or at least so far, complexity for both those cases. But that's really hard to get, unless you are willing to trade lots of memory and like double store everything. Then you might get close to the performance you want. And there's also a difference here between the mutable one and the immutable one, as we'll see. So the most essential operations for a seq map is, you have to be able to add entries, and they're always appended. So when you add a new key value binding, if the key isn't already present in the map, it's always appended at the end. And when you remove elements, you can remove, of course, the first one and so on, but you can also remove by key. And that could be potentially in the middle of the map, or it could be by index, like you index into it like a seq. And retrieval can be done by key, of course, since it's a map, but also by indexing. And all iteration or all traversals need to be done in order. So we'll have a look at the different types of the implementations. Yeah, and before we have to say that there's lots of prior art here. We have some in Scala already. Haskell, of course, has implementations, as well as Java. Yeah, the Kotlin, they all have different implementations. And of the ones I'm going through today, we'll see that, yeah, some of them, they don't all use the same, because it's really hard to know. Like, it's different trade-offs for different implementations. We'll start with the mutable one. And yeah, that's basically just one LinkedHashMap. It's a really good, it has good performance, doesn't take that much more memory than a regular hash map. And it's been around in Java since 1.4, and in Scala since 1.0. As I had to check that, but yeah. And the entries of a LinkedHashMap form a doubly linked list. Since it's mutable, you can have a doubly linked list. That's really, it's impossible for an immutable one. But for a mutable one, it's fine. And lookup is done the same way as for an hash map. But the entries in the hash map point to each other. And traverser becomes very performant. You just follow the next reference to the next entry. And so you don't even have to, you can just fetch the first one and then walk the references to the next all the way till the end, if you want to traverse it. Removals are simple. Yeah, you update the previous next entries, so they point to each other, and you skip the one in the middle. And the Java implementation supports both insertion, of course, but also modification and access order. Being immutable, it can update its internal state on access, and then you can use it like a least recently used map or a cache or something, which is commonly done. The immutable implementation, or the set of immutable implementations, because there are several, there's no known perfect strategy, so it's really, you have to make a trade-off. Different trade-offs gives different performance or memory usage. And as I said, there are very many, or considerable amount of different implementations that exist in these different languages. There's one strategy for implementing these kind of sequential maps that are, you can see it in several of the implementations, and that is to use a hash map for the mapping side. You keep key to value, maybe with some metadata, and then you combine that with an ordering of the keys. That means that you will have a certain amount of double storage, because the keys will be referenced from two distinct data structures. One used when you traverse, and one used when you just want to see them, get the values. And for immutable data structures in general, trees are really nice, because you can make a new, like if you add something, you can use almost the entire tree or perhaps the entire tree for the new one. So it's not, you can reuse a lot of the nodes in the tree. And lists, you can see them as a one branch tree. So lists are also a good way of implementing these. So a couple of definitions before we get started. I'm going to use these as names in the following images. So when you see ABCD, it's basically that seq map. And when you see ABCDE, I have added like an E to E binding on that one. And ABD, then you remove the C binding or key from the ABCD. Yeah, you'll get it sooner. We'll start by list map. This is actually the oldest one in Scala since it's been in Scala 1.0. And the entries of this one form a single linked list. So it's basically a list, immutable list. You add the entries at the head. So the most recently added is at the head of the list. This makes adding really efficient. You just prepend something to a list. But it requires that you reverse the list before you can do anything else, anything index-based. So anything, all the operations you do on a list map that can't be described as a init last decomposition, they're really slow. But init last decomposition is fast. So if you can make your operation express it in terms of the decomposition of init last, then it's going to be really fast. So this is basically a list map. So you in this case you've added A, then you add B, then you add C, and then you add D, or the mapping D to D. So it's really simple. It's a linked list with both the key and the value. Yeah, and by the way, these nice pictures I'm going to use in my presentation, I can recommend that this ref tree. It's a really nice way of being able to display your data structures. You want to see how they look and behave. So if we look at addition, one of the important operations for a list map, we can see that when we start with ABCD, as usual here, and then we add E, the E mapping, we see that you can reuse the whole list and just prepend something to the list. So that's really, really nice. But when we have the removal case here, then we have to do a little bit more. So we remove, and then in this case, we remove the C element or binding. So the C here must disappear. So then we must restructure the list all the way. This part can be shared, but the rest can't. So ABCD here has a new pointer to this part. Yeah, sorry. So that's list. This is list maps. It's quite good in those cases, unless you want to remove something close to the start of the list, then you're going to have to reconstruct the list all the way up. Yeah, and this is one that's new in 2.13, the VectorMap. It uses a hash map for the mapping, and it uses a vector for the ordering. So the hash map contains not only the key and value, but also the index in the vector for each key. This means that when you remove something by key, you have to find which index is this located at, so you can remove it from the ordering as well. And this is also the default implementation of a seq map or immutable seq map in 2.13. It looks like this. This is a simplified picture. Did this disappear? Yeah, perhaps. No, there. So I'm going to use this form to describe the hash map. This is not the correct. In reality, this is quite a large tree-like structure for the immutable hash map, but I'm going to use this because for many of these implementations, they all use this kind of. To make the picture simpler, I'm concentrating on the ordering part because that's what's going to differ. And here you see the vector map. It has the mapping and the ordering. And in the ordering, you have the usual vector. And I've abbreviated here. So in reality, this array is 32 elements long. So when you have added A, B, C, D, you get a nice A, B, C, D here, and the rest are nulls in this long array. So when you add something to a vector map, you start with A, B, C, D there, and we add the E mapping. So reuse, or this one will be an updated hash map, but it will change or add a node here, but I won't show that, as I said. But the vector, it needs to build a new vector because it can't share this part with the earlier one, since it's still not the... If you have more than 32, then you could share the first part of the vector, but in this case, you need to build a new vector here. And for removal, this is interesting case for VectorMap. We have the vector here, and when we remove stuff, the new vector, it won't remove the C from here. You see in the third position we have a C. It won't remove it. Instead, it will insert a tombstone here that says that you have to skip this element, skip one element ahead if your index is 3. And the reason for that is that if we changed all the indexes, then this part wouldn't be able to share anything. Like then we would have to have a new, or we would have to map the entire hash map, because all the indexes would change. So to keep this part as stable as possible, we instead replace the C element with the tombstone here. Yes? So this is when this project, or during the 2013 work and the collection Strawman work before that, I initially created this one as a reference implementation, because if you think about this problem, like from the start, you might imagine that you have a hash map, you want to have this key to index and value mapping. So why don't store the keys in a tree map? That's going to be sorted, and you use an ordinal that you increase on each insert. Then you have one ordering from the ordinals to the keys, and you have the hash map as usual. So I implemented that and thought about having it as like a reference point for benchmarking and so on. And it basically looks like this. It's the same mapping here. Sorry, what happened? One moment. So this is the same hash map as an old. And this is the tree map, you know, with it's a red-black tree underneath, the immutable tree map. And here you have an ordinal. In this case, it's been increased to 4. So you have that node with 1 is the B, and yeah, so on. 0 is A, and then 1 and B, and 2C and 3D. So that's the layout. And when you add something to this one, you get a new. So it reuses some of the nodes. You see the 0 here doesn't need to create a new one. The rest here it creates, but it can reuse a certain amount of the nodes from the existing ordering. So that's nice. And when you remove stuff from this kind of collection, it's the same way. So you can reuse certain nodes here. From the new green one, it can still point to some of the nodes. So you have to create only those two and the representation up here. So it's quite good there. But the thing is that the tree map isn't optimal for this case. Like if you want to have a mapping from ints to keys, there is a better collection already in this Scala. And it's the int map. So this one is you only need to send in the key type because the int is already understood as the key. Yeah, so it goes from ints to keys, or yeah, in this case. And it performs quite good for all operations, but it occupies 50% more memory than VectorMap. So in this case, we trade memory for a little better performance, especially in some operations, as we'll see. So this tree-seq map, it looks like this in memory. This is basically a bit trie. So it has a prefix. These are all done on the bit values and a mask, and then it says like one branch to the left and one to the right. And they can either be tips or they can be composited nodes called bins. So you have the tips with the values and you construct it like this. And while it has quite a few levels, this one, which is why it takes more memory, it's also all the branching can be calculated by simple bit operations on ints, so they're very fast. So that's one of the good things. And when you add stuff to this, it looks like this. So this one also uses quite a lot of the old tree here. 2 nodes can be reused in this simple case, while adding a new one there, and those 2 intermediate nodes. And when you remove stuff, it's the same. The new one can keep using a lot of the existing tree here. And the last implementation we'll talk about is the Q-seq map. This isn't in Scala at all. It doesn't exist in the Scala standard library. It's just made for reference or for comparison. And this one uses a hash map K from keys to values for the mapping, and also a queue of the keys. And this is an immutable queue, so it's a little bit special. An immutable queue has a front list and a back list. And it builds, as long as you're building, it prepends here. And then it switches in certain situations and adds and the front and the back and reverses it. And then it can start again to add on. You can read more about this Chris Sasaki has written a book about these kind of data structures, and he mentioned it's also called a banker's queue. And the hash map is still the same there. So when you add something here, you have to prepend here. The E is prepended, so it's a new queue here. But it's this list should have been reused here. I don't know why it didn't. Maybe it's wrong with how it draws it. But in principle, it should be able to reuse it. And removal is the same. So you just remove the C and you get a new list. And now you see it's been switched to the front here while it was in the back there. And then we have another one. And this one is a bit special because this isn't one mapping and another ordering. This one instead mimics the LinkedHashMap. And so it's only a hash map, but instead of having the regular entries up here, it has an entry that also keeps the key of the previous and the next entry. So the difference towards the mutable ones is that the mutable one has a pointer directly to the entry. So it's just a pointer, the reference to get the next entry, and then you can continue the traversal. Whilst this one has the key of the next entry, so it needs to go to the top of the linked hash map and navigate once more down to find the. So if you traverse, you have to do lookups for each step. While in the immutable one, you can just dereference the next pointer. So that's a little bit more costly, of course. So you see here that the first key is A, the last key is D, and then it has a hash map here that has entries, where the value is in the middle and the previous pointer, or the previous key is to the left and the next key is to the right. So if you have no previous key, it's a special null value here. But here you see that you go by A, and then you find B, then you have to go up here and traverse again, and you find B. B is there, yeah. And you see that the previous entry here is A, and the next one is C, so then you go up one. And this hash match looks ordered here. That is just by coincidence. In this case, it's a hash map 4, and those are ordered, but in the general case, this will not be ordered by A, B, C, D. This will be like a hash order, so it's completely unpredictable. So when you add stuff to this one, it looks like this. So you see, we added the E, and now it came first here, so this isn't ordered. But still, you have the A, so you can go there, and this one reuses also quite a lot of the previous. They only need to change like the surrounding entries. In this case, the last one, because the previous last ones need to be replaced, and the new last one needs to be added. And when you remove stuff here, it's the same basic thing. You see, it can reuse much of the previous node or the earlier nodes while changing so it gets a new last one and so on. This actually looks wrong. I have to fix that. All right. So I hope you got a little bit of an understanding of how the different implementations are built up. And we're going to look at how I benchmark those. And when you benchmark in Scala, or Java for that matter, but especially Scala, there's a nice tool called JMH, the Java Micro Benchmark Harness. And it helps you, it's from OpenJDK, and it helps you avoid many common pitfalls in benchmarking. It's very easy to think you write a benchmark, like a micro benchmark, and it might be all optimized away or something if it's too trivial. So JMH provides you with tools to keep that from happening, and also because benchmarks tend to be pretty small and maybe do nothing meaningful, and then it's easy to get lost with that the just-in-time compiler optimizes away all your code almost. And if you're going to use JMH with Scala, there's a nice plugin, SPT JMH, that makes it very easy to run this kind of benchmark from SPT. And there's also a tool called the JMH Visualizer that lets you drag and drop your results file, a JSON file, into that, and it will draw all the diagrams and stuff. So that's really nice. And it also supports if you want to run your benchmarks on say on JDK 8, JDK 11, or with Graal or without Graal, those kind of stuff. So this is an example of a JMH program or benchmark. I don't know if you've seen it, but this is like the simplest possible. You say your sizes that you want to use, and then you have a subject you want to test, and then you initialize it in a setup method. So you create it of various sizes then. And then you define your benchmark as a method, like this traverse iterator. So get an iterator from the subject and then move through it. And down here you have a black hole here, the BH. And that makes it, that's there to ensure that the JIT see here that we don't use the result of the next here. So it could potentially skip this whole while loop. But by consuming it, we hide from the JIT what we do with it, so it can't optimize away the logic. Yeah, and this is the visualizer. I thought I might try to open this. So this is how it looks when you go there. You get like a screen where you can, or a drop area where you can drop your files. See here. You can start by with the memory. All right, if I can get drag and drop to work. So then it shows the with a staple diagram here. And here you can see that, yeah, out here is the name of the benchmark. So this is the implementations we have, like key-linked seek map, VectorMap, Q seek map, and so on. And here we see that for the memory usage, in this case, the tree seek map is it's quite bad. It uses a lot more memory than the other ones, like double the amount of memory almost of some of them. While the best one seems to be the linked hash map here. That's the mutable one, so that's really good memory-wise. And we also see that the important thing, VectorMap here, one of the default implementations, has quite good memory usage. If you hold your mouse over, you get like the actual figures and so on. So that's the memory, and we can do the same for some operation. Let me check here. I have lots of results here. We can take one like can take concatenating two of these arrays or seek maps together and look closer at that operation. If I can get this. Should have had a mouse. Doesn't seem to. Okay. Yeah, you can also load stuff from URLs and from GISTs. So you can publish your results on the net if you want to. Use this one instead. Just a moment here. Time, results. Like that. Yeah, we'll take some here. Concat was that the one I wanted? So this is an example of the concat. It's only for two sizes, so there's not many. There's only two, 163 elements and one for 4096 elements. But here you can see that the vector map isn't especially good at concatenating here. The value there is almost 1 million, while the fastest one is the tree hash seek map. It has like 370,000, and also the tree seek map is quite a bit faster than VectorMap, or less than half. So concat is one operation where there's quite a few differences, but the most operations are actually almost the same, independent of which. Can try another one here. Let's have like appending, maybe. So here's the time it takes to append, but these are really slow, really low numbers. So even though they seem to differ quite a bit, it's still almost the same. And appending is really fast for almost all of them. I haven't, list map is not included in these, because if you include list map on the operations where it's not any good, it's so slow that it's like skews the whole result. You see nothing else except list map. So I've excluded that from my runs. But one interesting result here. Let me load it. Where they differ quite a bit. And this is also the reason that tree-seek map is included at all, I think, in 213. Let's find. So, in this one, this is if you add elements and then you remove them in the same order you added them, then you will, for the vector map, you will keep removing indexes after one another in the arrays. And you have to replace those with tombstones that point to the, but when you have many such tombstones in a row, then you need to go, like it becomes like a linear update to change each one of those tombstones to point to the next, because the one they're pointing to is now removed, so you need to update the pointer one more and increment the pointer. And that's really expensive. So you see the vector map here has almost, you go to a logarithmic scale here instead. You see that the vector map has maybe, 440,000, no, million. And then you check the fastest one is tree-seek map here, and that one has 2.2 million. So that's quite a gap between those two. So yeah, that's one of the lessons you can learn from this benchmarking results. Let's get back to the presentation. It's there. Let me check. Yeah. So the conclusions. What conclusions can you make about these implementations? Well, I've said some of these, but list map is really fast for operations based on init last decomposition. So if you know that's what you're going to do, you can keep using list map. It's actually the best performer in those cases. But it's also really slow for anything else. And that's because it has to reverse the list on each operation, and that's quite costly if the list is growing large. Tree-hash-seek map is simple to implement. It's almost trivial to implement, but it's also quite slow and memory intensive. And that's why tree-seek map is an improvement of that one. Vector map is fast overall. It's a really good choice for everything except consecutive removals. So if you remove stuff in the same order you put it in, then it might not be the best choice. And the tree-seek map, it's on par with vector map overall, except for removal where it's very much faster. So but it requires 50% more memory than vector map. At least the version that's currently in 213 does. I've been working on an improvement that might get that down to 20% more or something. The key-linked seek map is promising, but I haven't added it quite recently, so I haven't done the most extensive testing on it, but it looks quite nice, and I believe that it might be you might be able to make that like a good compromise between vector map and tree-seek map. So it might be maybe for future Scala version, that will be the one instead. So that was basically the stuff I had about the implementations. I'm also going to speak a little bit about how it was to start contributing, because even though I'm using Scala for 10 years, I haven't been a contributor. Maybe fix some bug or something like that in a few projects, but I haven't had time to contribute more than that. But But I've been doing that now, and it started with the collection Strawman project. I don't know if everyone knows that, but that was like a test ground for new collections, the ones that are now in 213. And I got interested in that one, and I thought, yeah, that's really nice. And it was, I started developing a collection type there that I called spandex, but it wasn't. It was like the Ariseq. That's also a new implementation in 213, but it was circular, so you could append as well as prepend to it, and it supported write once mutation, which makes it really good in some cases or many cases, but also have some hard to handle corner cases. I did not succeed in getting it merged, yeah. So I continued instead because I liked to work on my spare time on Scala. So I got interested in the SeqMap work, initiated by Matthew de Dietrich, and I wrote this simple tree-map, hash-map based implementation to use as a reference for benchmarking. Then I started thinking of ways to optimize that implementation, and they ended up with the tree SeqMap, and that got merged in 2013. And the Scala community I found was very, very welcoming. The Strawman project especially was very, very nice to have as a starting point. And I'd like to thank Julian Richard Foy there. He did a good he helped a lot when you started out. So if you're going to have maybe those kind of the side projects are a good way of getting new contributors to start contributing. At least it was for me, because like instead of getting to know the full Scala, it's quite complex with all the modules and how the structure in the source tree and so on. You can start with something smaller and grow from there. And I always got good feedback and advice on any pull requests I made. The maintainers, of course, they're often quite busy or very busy. So they, of course, you can't expect immediate feedback. But I like if you ping them once in a while, they'll come around. Just be nice to them because they have so much to do. Yeah, that was basically it. So I'm thinking about taking some questions. Anyone? Yeah, thank you.
Yes. Did you explore this idea that you have like a mutable collection and then you switch it to become immutable? Like Ruby does that, it has operation freeze, and Clojure has something quite similar where you work with a mutable thing and then you make it in constant time immutable. Thank you.
Yes, yes. That's one way to. There's two aspects of that. One is that if you have a persisting, like a mutable collection, you can. We have builders in Scala, and those you can, like even for the immutable collections, you can. While you have that builder, you can use mutation and so on in the if it's an underlying array or something. And then once you call result, it knows now it's finished, so then it can return it. But then a common way of working with a list is that you have a list and you can append an item to it, and the old list is still valid. So you don't know if that's going to be kept on to be used. So you can't, if you have like an array seek that's an immutable array, you can't start even though the array might allow, or array buffer allows that you can put stuff in it, you don't know if anyone has a reference to the old states. You need to that state needs to be kept forever, basically. So that's one thing. If the API in Scala would have been more like that, you were forced to call some seal method at the end or something, then you might have, that's like the builder result method, then you would know that from here on, you can't change it, but up to here you can. When I did the spandex work, that actually changes behind your back, but it only does so if it knows that no one else has changed it before. But once it's changed, that slot will never be able to change again. So it's more like a write once. And the bad thing with that is that you, like if someone has a big array and writes something in a free slot and that becomes sealed, then if someone has the array that hasn't sealed that, or hasn't like one step further, if they try to write, you have to copy the full array each time. So that's quite expensive, and it might be surprising that adding one element is a really expensive operation. So that's a reason why it didn't get merged, I think. But thank you, good question. Anyone else? All right. Thank you.